Hello everyone. In this chapter, we are going to study the integral transforms. First section, we study the Laplace transform to solve a partial differential equation. Second section, we study the Fourier integrals. Third section is the Fourier transforms. First section is the Laplace transform. First of all, I will explain the Laplace transform to solve the partial differential equations. We consider the function of u. U is a function of two variables of x and t. Another variable of the x is treated as a parameters. X appears as a parameters. So we transform the t to the s. Transform of a partial derivative of with respect to t, it becomes s times Laplace transform of the u minus initial value of the u. And the second derivative, the very same ways, it's s squares, Laplace transform of the u minus su at t equals 0 minus partial derivative of u with respect to t at t equals 0. When we transform the derivative of the x independent of the Laplace transform of the t, it becomes the second derivative of the Laplace transform of the u with respect to x. Then we use these Laplace transform to solve the partial differential equations. As an example, we consider the wave equations. Wave equation is a second order partial differential equation. Second derivative of u with respect to t equals c squares times second derivative of u with respect to x. This is a differential equation that we'd like to consider. And as a boundary condition, at x equals 0, at x equals 1, displacement is 0. The initial condition, initial displacement is 0. The velocities of our strings is expressed as sine pi x. Under these boundary condition and the initial condition, we'd like to solve the wave equation. At first, we'd like to Laplace transform of the wave equations. So both sides of the equation, we just add the Laplace transform. C square is a constant value, so we can move the outside of the Laplace transform. So second derivative of the u with respect to t is expressed this one. So for the second term and third terms, initial conditions are included. Then if you substitute, u is 0, and then this is sine pi x. Initial conditions here. And the right hand side is a c squared times the second derivative of the Laplace transform with respect to x. Then we change this equation, it becomes a second order ordinary differential equation for capital U. We need to solve these differential equations, but this is ordinary differential equations. So we can use a method we learned before. So at first, we need to solve the homogeneous differential equation. This is equal to the 0. The solution to the homogeneous differential equations correspond to the first two terms. This is the solutions of the homogeneous differential equations. Then we need to find the particular solutions. So we can use a standard method to find the particular solution. The third term corresponds to the particular solutions. So by summing up the solution of the homogeneous differential equations plus particular solutions becomes the solutions of the ordinary differential equations. Then we'd like to determine the C sub 1 and the C sub 2 using the boundary conditions. Then we need to Laplace transform the boundary condition as well. So this u and the u at x equals 0 and x equals 1 both is 0. So Laplace transform also becomes 0. So capital U at x equals 0 and s equals 0. U at x equals 1, s equals 0. So from this equation, u 0 s becomes a hyperbolic cosine 0 is 1. So c sub 1. And the hyperbolic sine 0 is 0. And the sine 0 is 0. So c sub 1 equals 0. So from this one, c sub 1 equals 0. From the second equation, u 1s, if you substitute x equals 1, first term becomes 0. So c sub 2 hyperbolic sine s over c. And the sine pi is 0. So this is 0. So from this equation, c sub 2 equals 0. So we discovered c sub 1 and c sub 2 both 0. So solutions for the u is expressed as 1 over s squared plus pi squared c squared times sine pi x. To find out the solutions of the wave equations, we need to inverse Laplace transform of this one. So u is obtained the inverse Laplace transform of the capital U's. We multiply the pi c. Then we consider the inverse Laplace transform of this function becomes sine pi ct. So this is the solution of the u. So if you write a graph as a function of this is t and this is x, initially the displacement is 0. Because of the velocity is given, actually the displacement is produced with times. It's a change of the times. Also, we could use the method we learned, the separation of variable method. ux0 is 0. And the initial condition, round u, round t. T equals 0 is a sine pi x. So by applying the boundary conditions, you can find the solution of the u xt is given by n equal 1 to the infinities. A sub n cosine n pi ct plus b sub n sine n pi ct times sine n pi x. So to determine the a sub n, b sub n, you need to calculate. A sub n is a 2, 0 to the 1, ux0 sine n pi x dx. So this is 0. So a sub n becomes 0. For the b sub n, you can calculate 2 over n pi c integral 0 to the 1s round u round t at t equals 0 sine n pi x dx. So you can substitute initial conditions sine pi x, then it becomes 2 over n pi c into 0 to the 1 sine pi x sine n pi x dx. So when n is not equal to the 1s, this integrals becomes 0 because of orthogonality of the sine functions. When the n equal 1s, this becomes 2 over pi c 0 to the 1 sine pi x squares dx. This is becomes 1 over 2. It becomes 1 over pi c. Then you can substitute these relations into the here. As a solution of the u, it becomes 1 over pi c sine pi ct times sine pi x. Because the n equal 1 is only allowed. This is exactly equal to this solution. Okay, this is the end of the first session.